All right, folks, we got here Thursday, October 22nd, domain and range review with inequalities. So you're going to get some practice with domain and range today for a few reasons. One is that we're going to describe the domains and ranges of rates of change problems, situations you've been looking at, distance over time, and obviously speed changes in different situations. So you might want to describe the speed of somebody's graph from 0 to 5 seconds or 5 to 10 seconds and describing how far they went, for instance, for described range. So anyways, that'll be coming up on Friday. So that's part of the reason why you're doing the review of domain and range today. Also, second thing is to get some practice with inequalities. We haven't done much with inequalities this year much at all. And in fact, when we were writing about domain range, we'll say things like, yesterday came up like 0 to 6 was the domain, the first piece of that. Remember that graph where she fell down and she wasn't moving it for a while from like 6 to 8 seconds, so 6 to 8. We want to do that with inequalities. Now, if you remember domain, of course, if you remember domain, those are the x values, right? X values on the graph, all the allowed inputs into a function, and the range are all of the y values. Anything that comes out, everything that comes out, actually, like everything that's possible to come out is considered part of the range. So let's get ahead and dive right into it. You got your first slide right here, and this is called exploring domain, okay? If you're exploring domain, are you exploring the y values? Or are you exploring the x values? Well, let's check it out here. All right, a mathematician says something is wrong with the shading on this graph. What do you think it is? Well, we shaded the graph. We haven't done that this year, have we? We haven't really done that shading of graphs much this year. What the heck is going on here? I don't really know. What do you think it is? I can't draw on this. One of those drawing ones here. So anyways, also one thing I want to say is you're welcome to try this assignment by yourself, trying to try it. But like, I'd recommend kind of maybe doing it with me, have it open. I'm going to be going through this kind of slow so you can kind of just be thinking through it, right? Thinking through it, doing it along with me and seeing if I'm doing roughly the same thing that you're doing. That's my recommendation here. So anyways, let's look into this. Okay, exploring domain. All right, well, we haven't shaded it all. And then I see this figure down here. Oh, interesting. What kind of a graph does that look like? Well, for me, at least, this kind of looks like half of a parabola turned onto its side, okay? Here's where we want to get good at like describing types of functions, types of graphs, is that you sort of notice things, right? Notice patterns and whatnot. And for me, this looks like half a parabola turned on its side. So if you know anything about half a parabola turned on its side, you know that this looks like part of a square root graph. So this looks like part of a square root function, but it looks like the domain of this square root function is limited. So if we looked at this here, it looks like the domain of this function here, again, let's ignore the shading for a second. This function looks like it starts at x equals 1 and x equals 1.5, 1.6, 1.7, 1.8, 2, right? 2, 3, 3.1, 3.2. It looks like it goes all the way up to 4. And one thing that I noticed here, and another thing that we haven't really seen recently, is that I have an open circle right here. It's an open circle. We'll get to that later. And then this is a closed circle. We'll get to what that means later. But what is the deal with the shading? Well, it says exploring domain. Guys, if we look at this figure right here, where it looks like this is sort of a square root graph with its domain limited to values below 4, but then greater than or equal to 1, how does the shading interact? Well, it looks like the shading is going beyond where the domain ends, right? Going beyond the function, okay? So I would say what's wrong with the shading. So it looks like we wanted to shade from the beginning of the function to the end of the function, but it looks like we went too far. So I'm going to say this. I'm going to say this for my answer. You're welcome to put this down too. Is the shading looks like it's going too far to the right, okay, beyond where the function ends. Okay, so I'll put it here. If the shading, right, I'm making a guess right now. If the shading is trying to describe the domain of the function, then it's describing too many x values, right? Because we go up to about 4.6 or so, 4.7, and we start at 1. That's fine, but we're going a little bit too high. Okay, so I'm gonna share that with the class. You're gonna see other people's responses tomorrow, and you're seeing this video here. Okay, we got 15 slides to go through, guys. So this is probably gonna be like classwork. You have the 25-minute asynchronous class, and then you're probably gonna have to do like maybe 20 minutes for homework. Yeah, you get it done. You'll be fine. You always do. You get it done. You get pat you in the back. You got this. All right, fix it. Mathematicians use this type of activity, this type of shading to represent the domain of the function. Okay, that makes sense, right? We're doing we're starting right here and going all the way to over here, right? Because remember, domain are your x values, right? You start at a low x and then you go up and you end at the top x, and that would represent your domain. We don't care about how big or how small the y is. We just care about how small or big the x values are. Okay, so we got to fix it. Mathematicians use this type of shading to represent the domain of the function. To exactly measure the domain of a function, we include all of the x values that the graph crosses. Well, it's crossing too many here for describing domain, so we got to drag the orange points to fix the shading for this graph. Continue to the next screen when you are finished, okay? So I think it's going to be as simple as, tell me when to stop, this, okay? I think that, right? So it looks like from -1 to 4, and we got to talk about this closed dot thing in a second and the open dot thing in a second. We're going to talk about that, but I'm going to go with that as my answer. Let's keep going here. Boom. Write the inequality. Great job. You fixed the inequality on screen 3. I hope you did too. I hope you got that correct. Hoping it's giving you this answer here. And then it says it's hard to get the domain exactly right by moving points. So the way we want to describe domain isn't just like I see it start, right? So our domain starts here and it ends here. We don't just want to describe where we see it in the graph, like it starts here and ends here. We want to get a little bit more precise with that. And it says here, mathematicians use inequalities to describe domain, because they're more precise than just like shading a freaking graph here. Okay, so anyways, here's the inequality for the graph that one of your classmates created on screen 2. Help them out by fixing the inequality to correctly represent the domain of the function. Well, I think that looks pretty good. Here's an inequality for the graph that one of your classmates created on screen 2. Help them out by fixing the inequality to correctly represent the domain of the function. I think that looks right. What's wrong with that? -1 is less than or equal to x is less than or equal to 4. So, yeah, I mean, I think that, I don't really know where it's going with this, but here is x equals 1. There is x equals 4. Oh, it's going a little bit further. No, it stops at 4, and it doesn't include 4. So I think I'm just going to submit that, and that's what I got. Help me fix the inequality to correctly represent the domain of the function. I'm confused, to be honest. I'm being perfectly honest right here. It starts at 1, right? This graph starts at 1, and then the domain gets bigger. Look, it gets bigger. Oops, not going up there. I'm going to touch the actual function. Here's the actual function here. Starts at 1, and then it gets bigger to 1.2, 1.3, 1.36, 1.46, 1.5. All this is part of our domain, right? So they're all the x values here. Look, the x value on my graph right here, I'm pointing with my other finger here, my other finger down my pen. My x value here is like 2.16. So that means 2.16 is part of the domain. We can input to 2.106 to whatever this function is. We can now put of, I don't know, about 1.65 or something. Anyways, if we keep on going, right, all these values, every value between 1 and 4, look, 2.5 is part of our domain, like these are all parts of our domain, all the way up until 4. Okay, all the way up until 4 here. But the 4 is not opened up here, okay? Sorry, it's not closed here. So this is one thing that I want to point out. Maybe I'll do this real quick, and I'm going to add some time to your video right now. I'm going to take a screen grab of this. Maybe we'll look at this on Notability real quick. So I'll go to Notability. This is some stuff I was doing for Geo. Insert photo. You guys are like, I'm fast forwarding now. Fast forwarding. No, don't fast forward. Hang out. Do this with me. Mr. Fortin's got to do it. You got to do it too. Let's see what we got here. All right, so let me check this out, or let's check this out together, just to point it out here. So this here is right at when x equals 1. So remember, this is our x-axis here. So our lowest x value is 1, right? Lowest x value is 1. So our domain, all of our x values are in this section right here. That's where our x values are going to be. So that means that x can be 1, right? It can be 1. This is what this solid line means, right? Solid line means, and this is what a closed dot means is here. So what we call this, we'll do this hopefully next semester, review inequalities, but a closed dot, okay, what we see is a closed dot right here. That's actually called this. It's called a closed dot, and it's something, a closed dot says that that point is inclusive, okay? Something called inclusive means we include that point we see in the graph, in the domain, right, as part of the function. Inclusive, okay? It's inclusive, right? Try to know that one. That'll definitely come up for sure. An inclusive point right here is because it's a closed dot. Over here, This is an open dot. So what that's supposed to show you is that your values on the function, they start at 1 and they keep going and they go all the way up until 4, and then 4 is not included, okay? So right before that 4, we have 3.5, 3.6, 3.5, 4, 5, 7. It goes all the way up 3.67, 3.7, 3.8, 3.9, 3.95. Oh, and then we get to 4, right? Then we get to 4. And it actually says undefined there, right? Because 4 is not part of this particular function, right? 4 is not part of this function, right? We have an open dot there, okay? We have an open dot there. So here, right, just to give you a little bit of heads up on what will be coming next semester, we have this here. This is something called an open dot, right? A O is an open dot, right? Because it's a circle with seating inside of it. Open dot, and that is something called non-inclusive. Non-inclusive. Okay, so anyways, I'm spending probably a lot of time on this one because I anticipate people getting confused when they get to this slide. But this is non-inclusive right here. So that means that 4 is not included in this actual function right here, in this actual function. So it's not included, but everything else is, right? Because we have values starting here and going all the way up to where we see that circle there, and then it ends here, okay? So from 1 all the way up until 4, we have X values, but this is gonna be a less than or equal to symbol. So 1 is less than or equal to, right? To the X, remember this is like an alligator, right? Eating something that's bigger. He only eats the bigger thing. It's not gonna eat the 1 because X is always greater than 1 unless it's equal to 1 too, which is less than 4, okay? So this is our domain right here. And this is a less than or equal to symbol because this is a closed dot, okay? Closed dot is inclusive, so it's either gonna get this symbol or it's going to get this symbol greater than or equal to. So here it's less than or equal to because the X's are bigger over here. And then non-inclusive gets either this symbol or this symbol when you have inequalities, okay? It gets that here. So anyways, this 4 is not included here, right? 1 is included. So it suggested this as my possible answer, and I'm going to agree with it. So I don't know where they're going with that one. Hopefully you don't get too confused on it. Okay, I'm spending a lot of time on this video. I want you to make sure you watch this video and do this assignment. So I need to go faster, else you're just going to turn me off. So let's just check it out here. Fix the inequality below to show the correct domain of the function. Well, this here is a little bit easier now that I've talked you through it. Let's do it. Let's slide it over. Oops, are we able to slide it over? Oh, I got to fix it here. Well, it looks like okay, so if I can actually type on it, actually press on it. My lowest X value is at negative 1.5. Look at that, right? We're going from left to right. We read graphs from left to right. So we're going from negative 1.5, and I'm going to adjust this here. Negative 1.5 is less than X, and it looks like we get negative 1.5. Ooh, it goes all the way up to negative 0.5, 0.4, 0.3, 0.2, 0, and then we go above 0, right? Because we pass the y-axis. And then 1.6, 0.7, all the way up to 1. Okay, so that's where we're getting a little undefined action. That's not, there's no point there, right? This is an open dot. In open circles, there's no point. X never equals 1. That's part of the function because this isn't technically a point. This is an open dot. It's supposed to represent everything goes up to that. We can be 0.96, 0.97, 0.98. Those are all part of the domain. 0.98 is here, right? But 1 is not part of the domain. So we need to do this. Negative 1.5 is less than X, or not less than. It should be less than or equal to. You can just type both at the same time. You can also go to the keyboard too. So if we do this, the keyboard right here, hit the keyboard, we have a less than or equal to symbol right there, or greater than or equal to symbol if you need it. Okay, it's less than or equal to X, which is less than 1. Boom, there we have it. Check it out. Did you get the domain? I hope you did. I got the domain. I got it. So here, right? Closed dot, inclusive. Open dot, non-inclusive. And that's why we did this less than symbol does not include values of 1. X is always less than 1. Less than or equal to symbol, right? Negative 1.5 is less than or equal to X, right? Because X could be 1.5 on this function. That's part of the domain. You're good to go. Go ahead and submit it. Move onward. All right, strict or non-strict. What the heck does this mean? 4 possible answers for screen 4 are shown below, which represents the domain shown to the left. Is this the same one as last time? It looks like the same one as last time. You can adjust the inequality in screen 4 if this helps your thinking. So I am the math teacher, so I think I'm right. So I'm going with this one right here. Explain your thinking. The start, that in parentheses, right? Because it starts, right? The start of this function is at negative x equals negative 1.5. And there is a closed dot on the graph. So x equals negative 1.5 is an acceptable input to this function. So it's inclusive in the domain. So it's inclusive in the domain. The function continues. So it's actually something called a continuous function, which you'll learn about a little bit later. The function continues, continues until x equals 1, but x equals 1 is not part of the domain because, right? See how many of these because statements here, right? Because to justify what I'm saying here, it's not part of the domain because there is an open dot, which tells us it's a non-inclusive point on the graph. Non-inclusive at x equals 1. Therefore, the inequality next to negative 1.5 is less than or equal to, because x can be negative 1.5, and the inequality next to 1 is less than, because x cannot be 1 in this function. Hopefully that makes sense. Does that make sense? Maybe reread it, maybe pause, think about it for a little bit. I'm going to share with class. You'll see your classmates' answers tomorrow. All right, let's keep going here. We got slide 6, domain challenge number 1. We're on challenges here. I hope you watch this video, right? Sometimes videos get hard at the beginning. Teachers like do things. They do an I do, we do, you do. And the I do is the thing that the teacher does, and it's always the longest. And then it's like we do, we'll do one together. We do a lot faster because you took the time, right? We spent time doing some very slowly ones. Then we can do the next one that we do a little bit faster. And then when you do it, you just do it really quick. That thing that teacher takes you 20 minutes to learn, to teach you sometimes, might take you like 30 seconds to do once you actually finally start doing them. So anyways, the hard part is hopefully done now. Hopefully we can do these ones together. Domain challenge number 1. What is the domain of the function? Enter your answer in the box below. Be careful of less than or equal to versus less than, and greater than or equal to versus greater than. So let's check this one out. I can't draw on this, unfortunately, although it tells us here. Check it out. So we got negative 5, negative 3. So remember, it's x comma y, x comma y. X comes first in the alphabet. So our x is negative 5. See negative 5 right there. And it is continuous, right? It is continuous. This function just keeps continuing, negative 1.8. All these x values are part of our domain, right? These are all inputs to this particular function. 3.2, 3.33. It goes all the way up. Oh, it says undefined there, but I think it was just off the function right there, 4, 0. So this is completely continuous. So I'm going from negative 5 all the way up until, it's not going to show me, 10, but 10's undefined, right? Because we have an open dot, and that means non-inclusive once again, okay? Try to get better at these words that I've been telling you each time I say them here. So we got negative 5, and I'm going to go to this maybe keypad right here. And check it out, is less than or equal to x, which is less than, was it 10? Yeah, it was 10 right there. Less than 10. Check it out. I've found my domain. Yes, I feel good about this. Dashed line here, because this is, dashed line actually means non-inclusive as well. And we're going to open not there. And then solid line here, because this is inclusive here. So from anywhere, x is definitely, when x is negative 5 in this function, the output is negative 3. So we know it works. When x is 10 in the function, it says 10.3. Oh, that's part of the domain showing here. Yeah, we don't want that. It's undefined, as we saw earlier. So it's just a less than symbol there. submit, and there we go. Let Mr. Fortin know what's going on. If not, you're asking questions or emailing me if you don't know how to do this, because then I'll be like, oh, did you watch the video? Anyways, so this one's a little bit easier. Again, hey, these get faster as you do them. Thank you, guys. The hard part was done. Let's me blabber on. You got these teacher moves and sample responses. Mr. Fortin doesn't need that. We're all good. -6 all the way up to 8, and we're good to go. So -6. And this is inclusive, right? It can include x can be -6. We want to say that x isn't just always larger than -6, because that would be a lie. X is sometimes -6. Look, when it's -6, we have an output of -1.78. And of course, all these points are larger than -6. -1 is larger. 1.5 is larger than -6, right? So anyways, x is larger, is greater than or equal to -6 if we're reading it from right to left. We're reading from left to right. -6 is less than or equal to whatever x is, because x is usually larger than -6, all the way up until we have 8. Okay, we have 8 here, and then that's inclusive as well, because we have a closed dot right there. We have a closed dot. Okie dokie, let's keep going. Ooh, what's this? Oh, interesting. A piecewise function will have more than one piece for its domain. Oh, good God. Oh, good God. A piecewise. So you're telling me this whole thing is a function? Let's see here. I see 3 different pieces. Oh, I think I get it, right? Piecewise functions is a function, right? Piecewise, what do we see at the beginning of piecewise? Piecewise function, okay, is what? A function that's made up, I'm going to switch my stylus here, made up of a, so it's still a function at the end of the day. It's a function that's made up of multiple pieces. Pieces, yes, pieces indeed, because we see piece here, right? That's what a piecewise function is, okay? So piecewise functions are come up later in your textbook. You're like, man, there's a lot of crazy stuff in algebra. There is, but hey, it's not too bad. Piecewise function, pieces here. So here we're gonna have 3 continuous parts of our domain. One continuous part, another continuous part, and another continuous part. So there'll be discontinuity in between the 3 parts, but at least we'll have 3 parts here. So a piecewise function will have more than one piece for its domain. Drag the points on the x-axis to adjust the domain for this function. Continue to the next screen when you're finished. So let's do this big piece over here. It looks like this one might keep continuing, huh? Well, I think this one actually needs to go here because this one's inclusive. And this domain is inclusive. Like, so the reason why I know that is, look, this is a solid line right here. I know that my solid lines, if I've been paying attention to my last few slides, the solid lines go with the closed dots, right? Closed dots, because that means those points are included. The solid line means, hey, we don't care what the y values are. This is what our domain is, right? They include the boundaries. These are actually called boundary points, believe it or not. Boundary. There's a boundary point, a closed dot boundary point, and an open dot boundary point. All right, let's keep going here. Let's keep rocking on. We need a closed dot for right here. So I got the solid line for the closed dot, and then I have the dash line for the open dot, and boom, we got it. We got it. Yes. Okay, and then here it looks like we don't know how this ends. So I don't know if it's dash or whatever, but this is the only one where could potential, because we don't see any dot over here or anything like that. It's probably, I guess, this is the dash one and double dashed here, and this is dashed here. Okay, so this looks like what the domain is here. Look, it goes from here to here, then it stops for a little while. There are no inputs. Look, we look up and look down. There's no inputs around like -2 or so, -2.5 or so, and there are no inputs around like 4.5 or so, or 4.2 or so, and then it picks back up around 5 and keeps going. It keeps going. So anyways, there's domain challenge number 2. Let's see what we got here. Man, you're thinking like, man, this is a long assignment. I'm bored as heck. Let's just get done with it. Just watch the video with me. If you watch it for 25 minutes during class, then 20 minutes afterwards. Let's see, how long has Mr. Fortin been going for? Let's see what we got here. I'm tired too. Oh, 23 minutes. This hasn't even been that bad, guys. Wow. You're going to deal with so many you're going to lull. You're going to deal with so many lectures and long classes over the day, the ages that you're going to be here at the school. A lot of lecture here. Okay, write the domain for the function below using inequalities in the rows below. Use a new line for each region of the domain, each piece of the domain, how we want to call it. Okay, inclusive. So here we're going to go from -6 is less than or equal to x, which is, and then again here my keypad's down here. It says show keypad, so I can do this, less than or equal to -3. And there we go. We got that domain. Check that off the list here. Okay, non-inclusive, although it's telling us the points in this one, we know not to include that. This is false, right? -2. When -2, y isn't 6 for that part of the function because there is no output there, right? Even though this open dot is at -2, 6, that's not part of the function. So we're not going to include -2 in the domain. So -2, and we're just going to have the less than symbol. So I'm going to choose this one instead. Oops, -2, not -x, is less than x, which is less than, what's this? Oh, -1. Okay, good. -1. There you go. And finally, my friends, we have the last one here. It's pretty clear that that's 1 to me. What else don't you? So we go 1. We're scaling 1, 2, 3, 4. See, 4 is here. So this is 1. And that's going to be less than, not inclusive, because, right, we have an open dot right there. That's not a point on the graph. Like the open dot's at 1, 0, but the output of the function is not 0 when x equals 1, because at 1, it doesn't go into this function, right, because it's an open dot here. So 1 is less than x, which is less than or equal to, because this closed dot is inclusive, right? I'm going to say inclusive and exclusive a whole bunch here, right? You might as well learn them now. 3, and then we are good to go. Look, we're describing the domain. Yes, we got it. This is how a mathematician will write out the domain, right? They'll write it out like this. They'll write it out using inequalities like this. Or they'll actually do something called interval notation, which you'll learn later. Learn that in calculus. You're all good here. Okie dokie. Number 10. So we haven't explored range. You might be thinking, hey, I got my domain. Do I have my range? Domain in range, domain in range, domain in range. So we've been thinking about the x values so far because we're thinking about what the domain is of these relationships. Let's describe what the outputs are, shall we? Shall we? Let's do it. Okay, so now we will identify the range of functions. The range is the set of y values we get after substituting all of the x values into a function, right? We put in any x value that we could possibly put in. We put in all of them, the set of all x values that can go into a function. These are all the y values that can go out, that can come on out of that function, and that would be the range. What are all the y values that are going to come flooding out once we've tried all the x values? So here, we've tried all these x values. This looks like a parabola, an upside-down parabola. And it peaks, right? We have a vertex at 2, 1 here. So it looks like all of our y values, right? We can put in all these x values, and we're going to get all of these y values as our outputs here. So, and it's going to top out, right? Highest output is going to be 1, it looks like. Yeah, 1, right? So all of our outputs are 1 or below. Okay, 1 or below. So let's check it out here, what they say here. The range is a set of all y values we get after substituting all the possible x values in the function. Notice that the range of this function is y is less than or equal to 1, not y is less than 1. Why? Well, I don't see a closed dot, but yeah, I don't see an open dot either, right? I don't see an open dot either. So it looks like this vertex here is at 2, 1. So when an x is the input of 2, y is the output of 1. So that means that 1 is inclusive to the range, right? Because the y is 1 there on the function. So even though there's not a closed dot placed at 2, 1, we just see just a curve, right? Curve. These are all dots, right? Remember, these are infinite amount of dots next to one another. Every point along the curve is a closed dot, right? So every point along the curve is a closed dot unless you actually see an open dot. If the mathematician or whoever's doing this here is setting up the function puts an open dot there, that means that one point is excluded here. But if we see a curve here, these are all closed dots. Okay, got that? We're clear on that? All right, we're good to go. All right, number 11. Drag the blue points to identify the range of the function. Ooh, now we're thinking about vertically. What's our lowest y value to our highest y value? Because again, this is the y-axis. The y-axis is the vertical axis. We start low and high. We're going to start low on this. Let's do this, okay? So down here, looks like the lowest y values right there. And it's inclusive, so we don't have to worry about excluding it, right? So this is it -5? Is that where the range starts? No, you silly. That's an x value. X is -5. The y value, the lowest y value is at -3. It is. Look, it's at -3. And then it goes all the way. Wait, does it go up to here? Wait a second. Wait, this is a dashed line. So that means my range should go up to a non-inclusive point. So I should have an open dot. And I do up here. Look at that. Yes. Sweet. Rock on. So this is my range, right? This is my range. I'm going from -3 inclusive. So -3, right? -3, not -5. -3 is my y value. -3 is less than or equal to y. And y, which is less than, right? Less than, not less than equal to, just less than 3. There we go. Let's do it. I hope they ask. No, they not have me write that out as an inequality. Come on. All right. Fix the inequality below to correctly show the range of the function. Let's check this one out here. All right. Well, this is where it starts, right? This is where the beginning of the function is. If we're reading graph from left to right, which we do, right? We read graphs the same way we read books, from left to right, right? Or read a paragraph. We start on the left side of a sentence and read to the right side. So this is where we'd say the function start, but it decreases first. So that's going to change the range, right? Our lowest range value is, we got to look to this. This is called a local minimum, actually. And then this is also called a local minimum. And both of these are minimum points, it looks like. They're both minimum points. This one has 2 minimum points. Our lowest y value is -2. It's -2. And it's non-inclusive. So they have the non-inclusive less than sign here. So this is going to be -2 is less than y. Oh, and I can't see anything because this is -4 there. That's ridiculous. -2 is less than y, which is less than -4. That makes no sense. Let's change this to +4 for a second. Oh, that's too high. So now we got a little closer. -2 is less than y, which is less than 4, sure. But hey, you know what? We don't go all the way up to 4. We don't even go up to 3 on this graph. We end before that. We go all the way up to, looks like it's 2. Looks like, there we have it. There we have it. Wait, Mr. Forden made a mistake. What's the mistake that Mr. Forden made? Let's check it out. There we go. Done and done, because we see a closed dot here. Even though we didn't see a closed dot here, we would assume right here, yeah, this old local maximum here is part of the function. We don't see an open dot there, so we know that all these points on the curve are closed dots. If we don't see an open dot, all these points on the curve are closed dots. So this is a closed dot up here. We have a local maximum at y equals 2. Several maximums up here at y equals 2. And yeah, that's where our range ends. And that's hopefully what you got too. Man, you liking this domain and range stuff? I'm loving it. Let's keep going. I'm loving it. McDonald's, I don't know, whatever gets you through it. Just be singing little crazy songs in your head. I don't know. But just limit yourself. Don't spend like an hour and a half on this getting distracted by your cell phones, getting distracted by your music you're listening to. Like, I'm getting distracted with this. I'm having fun. I'm like doing a little bit of stuff on the side, but I'm still going to get this done in less than 40 minutes. Remember, I was like thinking 25 minutes asynchronous class and then like 20 minutes for homework. So I'm thinking like 45 minutes of work for a day. It's not too bad. Let's check this one out. Write the range of this function using inequalities in the rows below. Use a new row for each region of the range. Let's check it out. Whew, what can we do? Well, this guy, let's check out this one. Well, this one we see that we start from left to right. This is our highest point right here. So we know that this one's going to go up to 2, and it'll be inclusive of the 2. So I'm going to do my less than or equal to. You can just hit the less than on your keyboard here. You see a little less than symbol on the bottom right side. And then if you hit the equal symbol right afterwards, it'll do that. It'll make the less than or equal to thing. So it's going to be less than or equal to. This left one here is 2. And we're going to have a little y there. And then here, this isn't our lowest point right here, guys. Right? We dip. We are decreasing all the way until here. X equals -4. X equals -4. Y equals -2. So -2 is our lowest y, and then we start increasing. Our y start increasing again. So anyways, this is going to be -2, and this again will be inclusive because if we don't see a dot there, that the parts of the curve are all closed dots. They're all inclusive. They're all included as part of that function that we're showing on the graph. Okay, there's one piece of the range. I put y. Why is it showing me? No, this is right because we're doing vertical range here. Oh, interesting. Check this out. Do I need to write an inequality for this one, guys, to describe the range? Do I need to write an inequality for this one? I wrote an inequality for this one. Remember, the last few guys were writing an inequality for each piece of the piecewise function. But hey, quick question. Why don't I actually need to write an inequality for this one? Well, this one, our outputs are all between what and what? All between 0 for our y all the way up until like 1.5 or so. So here we've already said 0 is less than or equal to y, which is less than or equal to 1.5, because here 0 and 1.5 are between -2 and 2. So here, right, this is totally still a function because every input has only one output, and it's okay for a function to have the same outputs with different inputs. So anyways, this is still a function. This is fine. Right? This is fine. So anyways, we don't need to write inequality for this one because the inequality we wrote for this one, look, we've captured that in the range. Look at our graph. We've captured that. We've captured that. We captured both these pieces here. We just need to write it for this one up here. Okay. We've got some undefined points up here. Undefined points because they're open dots, non-inclusive. I got to say that a whole bunch of times. Hopefully you'll just learn to say it too or know what it means when you hear it. And it goes all the way up to 6, it looks like, and it starts at like 5 for our outputs. So between 5 and 6, and this is non-inclusive. So I'm going to not have my equal symbol here. It's not going to be less than or equal to. It's just going to be less than. And then I have 5 is less than y is less than 6. Boom, we're good to go. That's our domain here of this particular piecewise function is -2 is less than or equal to y, which is less than or equal to 2, and 5 is less than less than y is less than 6. Almost done here, guys. Almost done. We just got Zeke making a claim right now, my friends. So Zeke's sitting at your table, I guess. Zeke's with you, right? We're not having this pre-social distancing world. I remember last year when I taught people the phrase social distancing. I was like, that was my math classes was like, okay, I'm gonna put a word on the board, the phrase on the board. You're gonna be hearing this phrase a lot over the coming year. And kids' minds were blown. They're like, whoa, what is social distancing? I'm like, you're gonna know soon. Sad. Anyways, before you were social distancing, maybe you were sitting with Zeke here. Zeke claims that the function to the left should have 3 shaded regions for its range because it's a 3-piece piecewise function. No, as we just saw, it's not, because the range of the leftmost piece would contain the range of the rightmost piece within its range. I think that's good. I think that's sufficient. We'll share with class. You're going to see other people's answers tomorrow. So in case you're watching this later. And hey, we didn't have a slide 15. We're just done right now. I think we stole this this thumbs up symbol from Facebook. We might get sued here for copyright infringement or stealing the icons from one of the largest companies in the world. It's a bold move by the Desmos people. But there it is. There you have it. My goal for you is for you guys to spend no more than 40 minutes on this, right? We got 25-minute async class. And hey, Mr. Ford had a little fun while doing this too. He got it done in 37 minutes. Not bad. Enjoy yourselves. Please, please, please watch this video. I know I'm saying this, but like if people are just like, I had no idea if I'm doing that. If you hear your group being like, what was that assignment about yesterday? Just be like, did you watch the video? Just watch the video. It's all good. And email me questions if you have questions, right? Obviously, I could always be just like, whenever I get these questions, I'm like, oh, that's right. I could have explained it that other way. And, you're never wrong by asking me a question. It's like, usually like, I could have explained it a little bit differently. All right, that's it. It's 10:33 p.m. I got to call it a night. Have a good day, students class. I will see you guys Friday.